Welcome to AI Paper Drop. I'm Alex.
And I'm Maya.
What if we could tell an AI agent it was going to fail a complex task before it even finished its first move?
Wait, like actually predict the failure before the mistake even happens?
Exactly. Not just guessing, but knowing it is doomed from the start based on signals the AI is sending to itself.
That sounds like a superpower, or a nightmare, depending on if you are the AI.
Well, for the people paying the electricity bill, it is a dream. Let's talk about the problem here. We're seeing more and more AI agents, right? Not just chatbots, but agents that can actually do things. They browse the web, they write code, they execute multi-step tasks.
Right, like the ones that can plan a whole trip or manage a database. But the thing is, those tasks are fragile. One wrong turn at the start, and the whole thing collapses.
Exactly. It is like a death spiral. The agent makes one tiny logic error in round one, and then it spends the next 10 rounds trying to fix it, but it just digs a deeper hole. And the problem is, we usually just sit there and watch it happen.
Which is incredibly wasteful. You are basically paying for a zombie session. The agent is technically still working. It is consuming tokens. It is using GPU power, but the outcome is already decided. It is just a ghost in the machine pretending to be productive.
And if you're running this at a scale of millions of requests, those zombie sessions are costing a fortune. They are an environmental and financial drain. So the question the researchers asked was, can we spot the zombie before it even starts walking?
But how? If the agent hasn't actually made a visible mistake yet, where is the signal?
That is the brilliant part. They stopped looking at what the AI says and started looking at what the AI thinks. Specifically, the hidden activations. These are the internal numerical states deep inside the neural network.
Okay, so instead of reading the transcript of the conversation, they're looking at the brain scans?
Exactly. Think of it like a race car. You can watch the car on the track, and you only know it crashed when it hits the wall. But if you have a high-tech telemetry system, you can see the oil pressure dropping or the engine temperature spiking long before the driver even feels it.
So these hidden states are the telemetry. They are the subtle smells of failure.
Precisely. The researchers built something called a recall controlled probe cascade. Now, that is a mouthful, but imagine it as a series of security checkpoints. As the agent progresses through the task, at each round, a tiny, lightweight probe checks those internal activations.
And if the probe sees that a certain pattern of failure is emerging, it just kills the process?
Right? But they didn't just make one giant filter. They made a cascade. They distribute these gates across the first few rounds. This way, they can be incredibly precise. They can set a global guarantee, like saying, I want to make sure 90% of all eventually successful episodes survive these gates.
Wait, that is an important distinction. They aren't just trying to be right. They're trying to make sure they don't accidentally kill the winners. Because if you are too aggressive, you might abort a session that was actually going to succeed just because it looked a bit weird for a second.
Exactly. The cascade manages the risk. It balances the desire to save compute with the need to preserve success. And the result of this is actually wild.
How wild are we talking?
They tested this on models like Quinn and Llama. For Quinn, they were able to save over 47% of the total inference compute while still keeping 90% of the successful outcomes.
Almost half the cost gone? Just by stopping the failures early?
Almost half. And here is the part that really surprised me. The internal signals are available way before the behavioral ones. If you only look at the agent's behavior, you're basically guessing for the first few rounds. But the hidden states? They can predict failure as early as the first or second interaction.
So the AI knows it is failing before. It even tells us it is failing.
Exactly. In some cases, over 60% of episodes become non-viable within just 2 rounds. We have been spending all this money and time on the other 80% of the task when the game was already over.
That feels like such a massive waste of energy. But I wonder, does adding behavioral data help? Like, if you combine the brain scan with the actual words the AI is saying, do you get a better result?
You would think so, right? But the paper says no. Adding behavioral features provided no further gain. The hidden states already capture everything the behavior reveals, and then some.
That is honestly a bit spooky. The internal state is just that much more honest than the output.
It really is. So let's zoom out. What does this actually change for the rest of us?
Well, for developers, it turns efficiency from a guessing game into a science. Instead of just hoping their agent is efficient, they can actually certify it. They can say, I have enough data to guarantee this level of recall.
And it opens the door to much more sustainable AI. If we can cut the compute of failing tasks by 40 or 50%, we can use that reclaimed energy to run more experiments, solve harder problems, or just lower the cost of the service for everyone.
It basically removes the penalty for complexity. If you know you can abort the dead ends, you can afford to let the agent try more complex paths.
Exactly. It is the difference between blindly running a marathon and having the wisdom to stop the moment you realize you're running in the wrong direction.
If you are enjoying this, follow or subscribe to AI Paper Drop wherever you listen. It really helps, and we have a new episode every day.
Paper by Kai Wan, Zai Huang, Ziki Zhou, Qinshan Wei, Xin Wang. How Sun. Produced by AI Paper Drop.